Doing okay? No? Is that what you said? No? Sure. Okay, that's the right answer. Yes, doing great. A couple of things. I sent out an email, but just let me remind you in case you don't check your email or whatever. The exam has been moved. Exam 3. It's now on April 17th. Is that right? 17th. That's the Thursday before Good Friday, the Thursday before spring break. And then also we're having a reading quiz today. It goes up to I think page 116. That anatomy and physiology of was it hearing or sound production? Speech. Yeah. And also, if you're going to do a presentation, you need to send me an email. What I say this week? Is that what I said? I've only gotten one email, so I know that there are more of you going to do that. So please send that to me. And the chapter review is going to be due on the last day of class. I think that's like May 7th or something, 6th. Kayla? Oh yeah, of course. I just wanted a summary of it. Is that what it said? 1,000 words? Yeah, 1,000 words isn't that much. I mean, you can say your name in 1,000 words almost. Huh? Oh no, it's more than a page. It's about 4 pages. 3 to 4 pages. Yeah, it depends on the font and stuff. But yeah, 1,000 pages isn't that much. I mean, about 1,000 pages. Yeah, that's a lot. Yeah, summarize, please. But I also want you to, pick one of the topics within it, and you know, your interest in it or whatever. You can bring in outside sources and what have you. Um, Seemed like there was something else, right? Is there something else in that email, or is that all? Huh? Okay. Did y'all get my email? Anybody? Yeah. Okay. All right. It's on Moodle too. If you go on to Moodle, you can find it. It's under the forum or whatever, under the messages for the class. Okay. We left off last time looking at these two expressions. I just want you to know how these things vary or how they change the frequency. And I showed you two different things. This is the frequency for the, make sure I started my recording. Yeah, this is the frequency for a mass on a spring, where K is the stiffness of the spring. So a bigger K means that your spring is more stiff. So like this thing has a certain stiffness. It has a certain value K. What about the springs on your car? Bigger or smaller K? Much bigger, right? Those are really stiff springs, so they have a much bigger K. And if I increase my K, then I'm going to increase my frequency, all right? Let's see, how can you imagine that? Well, if you increase the stiffness of the spring, your frequency increases. I can't think of a good way to imagine that. And if I increase my mass, what's going to happen to my frequency? It decreases, so you get a lower frequency, all right? Now, in a similar way, you can't really imagine this in sound because we're just talking about an oscillating spring. But it is still simple harmonic motion, as we've talked about, and sound is a type of simple harmonic motion. That's this repetitive motion that goes over and over again. Similarly, by the way, a pendulum is also simple harmonic motion, like sound. So if I have a pendulum, right, it repeats back and forth. And the period of this is also affected by very similar things. We're not going to actually write the equation for that, but a pendulum is also simple harmonic motion. And then we also talked about this, and this is sort of where we left off. And this is the frequency for a vibrating string, like on a guitar, right? And the frequency is affected by a number of different things: the length of the string, the tension in the string, and then what we call the mass density, which you can think of it as just the mass, but it's basically how much mass per unit length is that string. I play bass guitar. Did y'all know this? I've told y'all this, right? Like, does my coolness factor, does it go up with you if I tell you that I play bass guitar? A little bit? Like, you already thought that was really cool, right? I'm just waiting for some love here, okay? All right, so now, if I increase the length, that decreases my frequency. So a bass guitar has really long strings compared to a six-string guitar, which are shorter strings. And that's because if you increase your length, you get a lower frequency. And of course, a bass guitar is low, and a guitar is high. Like, woo, high. It's the opposite. You get it? Anyway, if I increase the length, the frequency goes low. And then also, if I increase the mass density of those strings, if I make them fatter, then they're going to have a lower frequency. Have you ever looked at the strings on a bass guitar? They're a lot bigger than the strings on a six-string guitar, on an acoustic or electric guitar. And that's because if I have a greater mass density, they're going to vibrate with a lower frequency. If I increase this, it decreases that. And then the tension, that's true for both any stringed instrument, that if I increase the tension, it's going to increase the frequency. So if you play a stringed instrument, when you tune it, and many of y'all play stringed instruments of any kind? Anyway, if you tune a guitar, if you increase the tension, the pitch goes up. If you decrease the tension with the tuning keys, the pitch goes down. All right, there are going to be no calculations with this, but I do want you to know how these things change with the various variables. Length and mass density, if you increase those, the pitch goes down. If you increase the tension, the pitch goes up. All right. Let's look at pressure waves. We have an autistic boy in our church. He's not a boy. He's 19, 20, 22 now. And he thinks I'm really cool. Like he always waves to me. And one time I let him play my guitar, and he really liked that. Lucas, some of y'all might know Lucas. Lucas Belron. He went to Thibodeau High. All right. All right. So let's look at pressure waves. Are y'all clear on that tension thing? Tension, mass density, length. I want you to know how they affect pitch. Okay. Don't worry about the function, the equation. That's not terribly important. Let's look at pressure waves. We'll come back and we'll have a few questions about this business. All right, so sound is a transverse wave, right? No, it's not a transverse. It's a longitudinal wave. And a longitudinal wave, the difference between that and a transverse wave is a longitudinal wave makes the medium go back and forth, whereas a transverse wave makes it go up and down. So remember we talked about the wave, and they write about that in the book? If you do a wave like a normal wave, like if y'all were to do this, like maybe if I said a joke, y'all could spontaneously erupt into a wave. Or some very interesting fact. I don't think that's ever happened at Nicholas, but that would be super cool if y'all could spontaneously erupt into a wave. No, you don't have to do it. That's fine. What? Yeah. So that's a transverse wave. You would be moving up and down. A longitudinal wave, like the book describes, is if you were to move closer together and do it like that. It would still be a wave, but it's a longitudinal wave. And sound is a type of wave called a longitudinal wave. All right? So the medium moves back and forth. That is the definition of a longitudinal wave. Sound in a gas causes pressure variations in that medium. Or just pressure variations in the gas. So when we have this longitudinal wave moving back and forth, we said this before, but we get areas of high pressure, pressure higher than the atmospheric pressure in the room, and then areas of low pressure when that medium moves apart, that where the pressure will be slightly lower than the atmospheric pressure in the room. And so if we were to draw the pressure here, you would have some places where the pressure is high and other places where the pressure is low. And this would be like our at this point, would be like our atmospheric pressure. High pressure, low pressure. And if we were to plot out the pressure, it would look like this, which looks a lot like a transverse wave. But here, instead of plotting the displacement, I'm plotting the pressure. And so we can talk about these sound waves in the same way as we talk about transverse waves. I call these areas of high pressure, I call these condensations. I don't call them that. That's what everybody calls them. These are called condensations. These are areas of high pressure. And then these low pressures we call rarefactions. Right? Condensations and rarefactions. The rarefactions are areas of low pressure. And the book talks about how this is an application of the ideal gas law. All right, the ideal gas law is PV equals NKT. Or you might see it also written, I think we wrote it this way, as PV equals nRT. These are basically the same expressions, just a different constant. But the ideal gas law, if you get a greater number of particles, as you do in the condensations, then you get a larger pressure. So in those condensations, you're squeezing more particles together because of the energy in the sound wave, and then that causes a higher pressure. So this is a good application of the ideal gas law, that if I get a greater number of particles within a certain volume, then I increase the pressure. Or you can think of it as if I reduce the pressure of a certain number of particles, reduce the volume of a certain number of particles, that's going to cause an increase in pressure. Both of those are occurring. You're either getting more particles within a volume, or for a given number of particles, you're decreasing the volume, and that causes more pressure. Right, like a balloon. If I take a balloon and I squeeze it down, I'm squeezing more particles into a smaller volume, and that causes a higher pressure. What I just said isn't exactly right. If I squeeze a balloon down, I keep the same number of particles but a smaller volume, that causes an increase in pressure. Ideal gas law. All right. Now, sound can also travel through solids and liquids, and it actually does it quite well. A lot better than in gases. We like to go to the pool a lot. And my boy likes when I try to talk to him under the water. Have y'all ever done this? Like you try to talk to somebody underwater? You can hear really well. I mean, it's very difficult to speak underwater for obvious reasons. But you can make noises underwater, and it's very easy to hear them because sound travels exceedingly well in solids and liquids. However, in these solids and liquids, if you remember back when we were talking about fluids and fluid flows, gases differ from solids and liquids in one way. You remember? Or in a very important way. Remember what solids and liquids are? This came into play with Pascal's principle and why Pascal's principle applied to solids and liquids, but not to gases. Incompressible, right. They're incompressible. I was reading a book the other day. It was this MCAT, this is an aside, but it was an MCAT prep book. Like they had MCAT test questions and what have you, one of the ladies. And they were talking about Pascal's principle. It was obviously not a native English speaker that wrote this book because there are a lot of grammatical errors. And they meant to say that gases or solids and liquids are incompressible, but they said that solids and liquids are incomprehensible, which is a whole different meaning. Incompressible is not incomprehensible. Okay, so solids and liquids are incompressible. That's why we can use them like in hydraulic systems, for example. All right, so while we might call a sound wave in gas, I don't know if I've used this word, but in gas we would call it a pressure wave. All right, or a, what was the other word I used? A compressional wave, a pressure wave, or a compressional wave. Did I use this term? Compressional wave? Okay. Oh, shoot, sorry. That doesn't make sense to call them that when you're talking about sound traveling in a solid or a liquid. All right, so we're just going to call them in solids and liquids. We'll just call them either sound waves or longitudinal waves. The sound actually does make the medium move a little bit back and forth, but since the pressure of these solids and liquids can't change because they're incompressible, then we don't call them pressure waves, or we don't call them compressional waves. We call them sound waves or longitudinal waves. The reason, by the way, that, well, actually, no, let me say one more thing. Sound travels at different speeds depending upon the medium. And this is dependent upon the elasticity. The speed of the sound is dependent upon the elasticity of the medium. The speed of the sound is dependent upon the elasticity of the medium. That is, if it's more elastic, I'll describe what that means in just a second, you're going to have a higher speed. If your medium is more elastic, you're going to have a higher speed. What I mean by elastic, well, it goes back to that spring constant. Right, for a spring, this has a certain elasticity. If I stretch it, depending upon how elastic it is, it'll go back to its equilibrium position. The more elastic it is, the quicker it'll go back to its equilibrium position. Or the more elastic it is, the harder it's going to be to take it away from its equilibrium position. All right? So if I have a greater elasticity, then that's going to lead to a higher speed. Let me ask you a question. Of these three, which is the most elastic? All right, so which of these? Can I go down from here? Oops. Of these three, I might repeat this question in just a bit. I forget if I put it on my other slide. Of these three, which is the most elastic? That is, which is going to return to its equilibrium position more readily? Is it going to be a solid, liquid, or a gas? Oh, shoot, I didn't know. Let me open my clickers right quick. Give me just a second. All right, which is the most elastic? Solid, liquid, or a gas? Of those three, which is the most elastic? And then whatever's the most elastic, sound will travel the fastest in that. So does sound travel faster in a solid? Does it travel faster in a liquid or travel faster in a gas? Which of those is the most elastic? Yeah, we will see this again later. So remember your answer. Most of you have it correct. I'm going to give you just a few more seconds. 55, I'll stop. All right, A is the right answer. solids are much more elastic than gas. If I disturb a gas, it's not going back to its position at all, right? Because it's off. You know, I do this, and then like the gas goes way over there. But if I disturb a solid, well, it's very difficult to disturb a solid, right? I can't really bend it very easily unless I actually deform it. And so it's a very elastic thing. And as a result, the sound travels much faster in solids than it does in gas or liquid. So for example, in your book, they give several speeds for the sound, the speed of sound. So for example, in water, sound travels at 1,500 meters per second. You don't need to know these numbers. I'm just giving them to you sort of for reference. By the way, this is about 3,400 miles per hour. In steel, on the other hand, which has like one of the highest speeds of sound, it's 5,100 meters per second, which is about equivalent of 11,400 miles per hour. And then in air, it should have the lowest speed, or 340 meters per second. And notice this is quite a bit even than the speed in water. And this is about 700 miles per hour, 760 miles per hour. All right. However, in a gas, you can change the medium to change the speed of the sound. So in a gas, you can do a few things. We saw this in a video. I think it was that Khan Academy video, where they talked about how you can change the speed of the sound. That if you change the wavelength or frequency, that does not change the speed of sound. The only way that you can change the speed is by changing the medium. And you can either change it to a different medium, like change it to steel or to water or whatever, or if you have a gas, you can do certain things to the gas. You can change its temperature, right? If you increase the temperature, that'll increase the speed. You can also change the density of the gas, or you can change the type of gas. So let me put this in words. In a gas, you can change the medium to alter the speed of sound. By the way, this is sort of true for solids, but less so. Like if I increase the temperature of a steel bar, it's not really going to change it that much so that you would change the speed of sound any measurable amount, because those atoms are so locked into their positions, they're not really affected that much by temperature unless you have very extreme temperatures. All right, so you can change the medium to alter the speed of sound. So for example, you could change the gas and smaller molecules of gas like our smaller atoms, like helium is just a smaller atom than say oxygen. All right, so actually in that video, in that Khan Academy video, they said you could change the speed by making it helium instead of air, which is made of much heavier atoms or molecules. So yeah, so smaller mass. You want to think about that. Smaller molecules of gas move more quickly. Just because they're smaller, they have less inertia. So as you might expect, they would have a lower or higher speed of sound? A higher speed of sound. Since they move more quickly, they're able to transfer the energy of the sound more quickly. So sound travels more quickly. So you can change the gas. You can also change the temperature. And a higher temperature leads to a higher velocity. This is probably intuitive to you, but if your molecules or your atoms have a higher temperature, they're sort of moving around more quickly anyway, and they're able to transfer the energy of the sound better. Right. But just notice you have a higher temperature, you have a higher velocity or higher speed of sound. Okay, for some reason, I'm not really sure why, but like breaking the sound barrier throughout history has been, or not throughout history, like in the 20th century, when we've been able to do that, has been a really big deal. So back in, I think it was the 50s, yeah, 1947, it was done by Chuck Yeager in a jet. He was able to break the sound barrier. And then just recently, back in the late 90s, it was done by a land vehicle, a jet-powered car. I'm going to show you a picture. It's called the Thrust SSC. It's really cool. And then also there was recently a big deal about another sound barrier. Do y'all remember what that was? What is it, Kylie? Okay, yeah, something from space would break the sound barrier. By the way, the space shuttle coming in from space often breaks the sound barrier, but I'm thinking of something else. Oh, yeah, a whip breaks the sound barrier. Does it say that in your book, or you just, yeah. Oh, okay, yeah, a whip. That's where you get that loud crack with a whip. That's a sound barrier. Or even like if you, when I was a kid, we used to do rat tails. You want to do rat tail? You take a towel, just a little bit wet. Wait, y'all are athletic trainers, man. You take one of those towels and you roll them up in a particular way, so you got this little thing. It hurts bad, yeah. But that breaks the sound barrier, and then you can whap somebody with it and say, "Hey, just broke the sound barrier," and then they wouldn't be mad at you. They'd just think, "Gosh, that's really cool. It hurts, but it's cool." No, there was a guy that broke the sound barrier. Remember that guy, the Red Bull guy? When he jumped from space, yeah. So he broke the sound barrier. And that was, I think it might have been the first time. What? He took a balloon and went way up into space, and then he jumped out. Isn't that super cool? Yeah, very scary. All right, but he broke the sound barrier. So anyway, we have this fascination with breaking the sound barrier. When a plane, or really when any vehicle breaks the sound barrier, you get a sonic boom. The sonic boom, there are lots of physics that go on in a sonic boom, but you can think of it in a similar way to the wake of a boat. It's really basically the same. Let me go to the next page, actually, so I have more space. May I? All right. So in a sonic boom, the vehicle, or whatever the object is, plane, car, boat, or not a boat, but a plane, car, man, whip, exceeds the speed of sound in the medium. Or you can think of this not just the sound, but of waves in the medium. So for example, if I have a boat that's going along with a certain velocity within the water, waves in a lake have a particular velocity at which they travel. And it's based on a lot of things. It's based on the temperature of the water. It's based a lot on the depth of the water. So you'll see waves as they come in, they'll actually change as they move to different depths of water because the waves will move at a certain speed depending upon the depth of the water. And so when a boat exceeds the, uh, the speed of the waves, it creates a sonic boom of sorts. It's not a sonic boom because we're not dealing with sound waves, but it creates a very similar thing. And what's that called when a wave exceeds the speed of the waves in a lake? What do we call that coming off of a boat? The what? Somebody said it. Rhymes with rake. Wake, right. So if it exceeds that, you get basically these waves. It starts catching up with the waves in the lake, and you get this effect where you get these waves that come off the side of the boat. And if you're standing on the shore, they make all up into a really big wave, and that's called a wake, when you exceed the speed of the wave in the medium. And so a similar thing occurs with a sonic boom. Uh, that's really all you need to know about the physics of that. I'm going to show you a couple videos that are kind of cool, I think. One is just about the sonic boom and some of the really neat things that happen within a sonic boom, because you get these pressure variations and some stuff can happen with the atmosphere. Y'all ever seen or heard a sonic boom before? Yeah. Um, if you've seen the Blue Angels before, They usually have a sonic boom attached to them because they go really fast. And then I'm going to show you just a very short clip of that car because it's just really cool. The car that broke the sound barrier. 700 miles an hour. Isn't that the speed of sound? 760 miles an hour. Huh? The Thrust SSC. Yeah, so you can find a clip on YouTube about it. No, what, the car? No, you can still hear it because the sound still travels to you from the car, right? But it might not be the same as what you see in the car. Like there might be a lag time. Well, no, that's not true. Never mind. Forget I said that. We'll see. We'll just watch the video. But you get this sonic boom. Let's see. Yeah, we'll watch this one first. This one is a couple minutes.